Hello everyone, today we're going to talk about regularization via early stopping. The prerequisites for this material are ordinary least squares and the analysis we did on the coefficients, the training and the test error of ordinary least squares, and also ridge regression, which as we will see is very connected with this topic. Okay, so probably most of you are familiar with gradient descent. Gradient descent is a very simple technique to minimize a certain cost function. Essentially what you do is, when you find yourself at a certain point, okay, so this is maybe a candidate for the minimizer, you check what the gradient looks like at that point, and you move down in the direction of the steepest downward direction, which is minus the gradient. So the idea is that you initialize at an arbitrary point and then you update this point by moving little by little down in the direction of minus the gradient, because again that gives you the steepest direction down. This alpha k here is a step size which you can change as the iterations proceed, or you can keep fixed, it depends. Usually you wait until a certain stopping criterion is met. For example, the gradient becomes very, very small, or you don't make much progress anymore, and then you stop, and that's where you have converged. Here we're going to see what happens when we apply gradient descent to the least squares cost function that we have talked so much about. So here is the cost function. We're going to expand it as a quadratic. And remember that we're doing least squares to basically solve a regression task. We're interested in fitting the coefficients beta. So this is a function of beta in this case. When we take the gradients, if you remember your multivariate calculus, this is essentially the generalization of beta squared. So what happens is basically that the gradient corresponding to this term is just the matrix that is multiplying the betas times beta, because again it's as if you had beta square except that we have vectors. And the gradient of this is just a constant vector inner product with beta. The gradient is that constant vector. Okay, so that's the gradient here. And we can write it like this, which is a bit more easier to deal with. So these are the gradient descent updates for least squares. We are at a particular point and we make progress by going in the direction of minus the gradient. This has, when we expand this out in terms of so remember that each column of X or rows of X transpose are actually examples of feature vectors. So if you expand this out in terms of those feature vectors, it turns out that you can write the gradient update in terms of each example as the residual meaning the response for that example minus the estimate in the linear model. And remember that here we're always dealing with a situation where everything is centered, so that's why the linear model does not have a constant term. Okay, anyways, this is the error that we make for that particular example, and then we add a multiple of that corresponding feature vector to the coefficients, and how we scale that depends on the error. And it's really intuitive, because if yi is bigger than the linear model, then this is going to be positive, and what we're going to do is we're going to add xi to bring the coefficients in that direction, which will increase the linear model and make it closer to yi. Okay, because see that beta k here is multiplying xi. If on the other hand the linear model is smaller than yi, then we do the opposite. We subtract xi to again bring the linear model closer to yi. So you can see these updates in a very intuitive, they have a very intuitive interpretation, and we might have come up with this algorithm to update the weights even if we knew nothing about gradient descent. Basically, we look at the error that we're making for each example and we adjust the coefficients using the corresponding feature vector to make that error smaller. Okay, this is what we're doing. Okay, so now we're going to analyze these gradient descent updates a bit more carefully. And in order to do that, it's going to be useful to write them in the following way. Okay, so this is the expression that we already derived. This is exactly equivalent to multiplying the previous coefficients by this matrix, which is 1 minus essentially a scaled covariance matrix of the features, plus this term that depends on the response. So let's see what happens as we proceed when we initialize at the origin. So we initialize with 0 just to make things simple, and we have a constant step size. So the step size is going to be called alpha. It's not going to change from iteration to iteration. So at first we start at 0. Then since this term is 0 at the beginning, we just get this second term. And then we multiply beta 1 by this matrix and we add this term. Okay, we're just basically applying this formula over and over. And what we see very soon is that essentially we get this term, then this term multiplied by the matrix, and then in the second iteration, okay, just applying the formula, we have this term applied by this matrix, this term multiplied by this matrix twice, and this is what's going to happen as we go along. So the general formula is that we have the feature matrix applied to the response scaled by alpha, and then we multiply over and over this matrix, which is the identity minus a scaled covariance matrix, and depending on the iteration, we apply it k times and we sum all of this. Okay, so this gives us a very clean expression for what the k plus 1 value of the coefficients is as we proceed with gradient descent. Okay, so now we're going to analyze this expression further that we just derived. And in order to do that, we realize here that we have this power, this matrix power. So when we have a matrix power, okay, this basically means that we're multiplying this matrix 8 times. This is actually pretty difficult to deal with when you have matrices, because matrix times matrix multiplication, it's not super intuitive to see what's going on if you multiply it many times. But it's much easier to see what happens when you have an eigendecomposition of the matrices. Why? Because when you have an eigendecomposition of the matrices, you can basically, so imagine that A is equal, imagine this as symmetric matrix just to make things easy, okay, and you have an eigendecomposition like that. You can write AI as ut times ut many times, and what happens is that these guys, because these are orthogonal matrices, if you have a symmetric matrix, you know that the eigenvectors are always orthonormal, or you can pick them orthonormal. All of these guys cancel out and you end up with U, the diagonal matrix to the I, and U transpose. And this makes life much easier because now essentially you just have a power of the eigenvalues in that direction, in the diagonal. That's what I meant, a power of the eigenvalues in that diagonal. So this is just much easier to deal with. So this is just to illustrate that a common strategy to deal with powers of matrices is to try to apply the eigendecomposition of the matrix, and then things simplify a lot. So that's what we're going to try to do here. The issue here is that this is a symmetric matrix. And of course, we know we've done this a few times in our analysis. If you apply the SVD here, the SVD of X, then you quickly realize that this symmetric matrix has this eigendecomposition, where the eigenvalues are just the square singular values of x. But now the issue is that if we're going to apply this kind of reasoning here, we would need this other matrix, the identity, to have the same eigenvectors, so that we can express their this whole thing in terms of an eigendecomposition that has the same vectors, so that we can apply this argument. We're in luck because you can always do this with an identity matrix. You can always write it as U transport for no matter what U, as long as U is orthonormal. Okay, it has orthogonal. I mean, it has orthonormal columns or rows. So that's essentially the strategy we're going to apply. We're going to say, okay, we have a power of matrices. We need to simplify this into eigendecomposition so that we can deal with it. We know that one of these terms in this linear combination has eigenvectors that correspond to the singular vectors of x. So let's express the identity in terms of those singular vectors also, and now things will simplify. Okay, so I just wanted to give you a quick reasoning behind the strategy that we're going to apply. Okay, so exactly what I said. We express the covariance matrix like that and the identity like that, and now the U and U transport can come out, and here we just have a diagonal matrix, so we can just apply the power to each entry in the diagonal. And this is what this means, okay? And we also, by the way, can bring the sum inside of the diagonal because nothing else depends on I, okay? Like the only dependence on I is here, so we can bring the sum into the diagonal. We end up with a diagonal matrix that has this sum in each entry of the diagonal. And now, if you look at this sum essentially says that we have a sum of R to the I from I equals to 0 to k. This is a geometric sum, and if you remember, this is basically equal to 1. Let me get this right because I always get this wrong. Minus rk plus 1 divided by 1 minus r. Okay, so you can look this up. This is just a simple geometric sum. Essentially, the way you derive this is you multiply times 1 minus r up and down, and then you expand the sum and you see that you have a lot of cancellations and you end up having something like this. Okay, so notice that this sum will converge to 1. This will converge to 1 over 1 minus r if this guy goes to 0, which happens if r is strictly smaller than 1. Okay, so just to be clear, our r here that we're talking about, our r is equal to 1 minus alpha sj squared, where sj is each of the singular values of the feature matrix, because again, this sum occurs at each point in the diagonal. For every entry in the diagonal, you have a different value for the singular values. Okay, but we can apply this geometric sum reasoning to all of them. So we end up with this. I actually got it wrong, got it right for a change. Realize that here r was equal again to 1 minus alpha sj squared. So that's why we got 1 minus rk plus 1 over 1 minus r. And then 1 minus r is equal to alpha sj squared. But there was also this s here, which we can bring into the diagonal to cancel out this square. Okay, so this is why we end up with alpha sj there. And now again, we're going to have that this converges to just 1 over alpha sj if basically this is smaller than 1. Okay, the absolute value of that. So I already gave this away. Sorry about that. I should have actually asked you so that you thought a little bit about it. But what's the condition for convergence here? To converge to a specific value so that this doesn't blow up. The condition is that this guy has absolute value smaller than 1. And in that case, this is going to disappear, okay? And if that disappears, we just have u, and then 1 over sj in the diagonal is just the inverse of s, v transpose y, and that's exactly equal to the ordinary least squares solution. So this actually shows you, without having to go into, gradient descent converges for convex functions, and this is a convex quadratic or whatever, this shows you immediately how the gradient descent iterates are converging towards the ordinary least squares solution, which is good because that's the minimum of the cost function. We have already shown that before. And the only thing that we need to take care of is make sure that alpha is small enough so that this whole thing is smaller than 1. Okay? And we can guarantee this just by making alpha smaller than 2 over the largest singular value squared. Okay, you can check that. Okay, so essentially alpha is going to, we're going to have to make alpha more or less like 1 over s1 squared. Okay, that's maybe I should have written kind of proportional to, the proportional sign is equal to alpha, so this is kind of confusing. So maybe let's say that we're going to pick an alpha that is more or less 1 over the largest singular value squared. And the reason for that is that we want convergence. Okay, so now we can ask, we converge, but how fast do we converge? Okay, how quickly does this term disappear? Because when that term disappears, then we have converged to the ordinary least squares. Now we're going to assume that we set alpha to 1 over s1 squared, because in general you want to have the largest step size possible to make a lot of progress, but not so large that you diverge. Okay, that's kind of the usual strategy in gradient descent. And then you realize that if you plug in alpha there, I plug in alpha here, alpha is 1 over s1 squared, this gets multiplied with sj squared, okay, and then we have 1 minus, right? So what happens here is, and this is what, that's k plus 1. So how fast or how slow this converges will depend on the ratio between sj, between each of the singular values and the largest singular value. Okay, so if you realize, the smaller the value in here, that is to the power of k plus 1, the fastest it's going to go towards 0. In order for that to be small, this should be as close to 1 as possible, which means that the other singular value should be as close as possible to S1. So it should be close to S1 so that this guy is close to 1 and the whole thing is small. So then the powers will decrease very, very fast. However, if some of these guys are very, very small, then this whole thing will be close to 1 and this will converge very, very slowly to 0. And indeed, this is what we observe. Here we have an example where one of the singular values is equal to 1 and the other one is equal to 0.1. So what happens is that we make very strong, very fast progress in one direction, which is the one corresponding to the singular vector associated to the to the large singular value, because essentially this term for that singular value disappears very quickly. But in the other direction, okay, it takes ages. So you have a first you make a lot of progress in one direction, and then eventually, like, you've already reached your goal in the direction of that singular vector, but then gradient descent takes ages to actually reach the ordinary least square solution because of the slow progress induced by that small singular value. Okay, and we see that over and over again. over and over again. For different examples, because remember that the ordinary least square solution, so here I should have said I'm showing you some examples for an additive model. Well, I did say it, right, that it's an additive model. And in the additive model, we have some Gaussian noise on the response, and because of that noise, the ordinary least squares is not at the same place as the true coefficients. We discussed this at length when we're talking about the analysis of the ordinary least squares coefficients. And here we see again that the point of showing you this is that gradient descent takes ages to get to the ordinary least square solution. Okay. For real data, so this is the temperature prediction example that we have been using, there are a lot of singular values that are small, even if you have a lot of training data. So this seems like bad news. You know, convergence is very, very slow because you tend to have some small singular values because you do have correlations between the features. But maybe we should stop and think a little bit, because do we actually want this thing to converge? Let's go back to the graphs. And I would like you to look carefully at the graphs and ask yourself, do we actually want gradient descent to converge? And, you know, think a little bit about it. Stop the video if you want. But we see that in many cases, when we have made this initial progress because of the large singular value, we actually have like quite a few points that are often closer to beta true than the final point. And intuitively, that's not, well, here it's just that the final point happens randomly to be on top of beta true, right? But this is not that surprising because we have learned that the coefficient estimate has a huge variance precisely in the direction of the singular vectors which are associated to small singular values. Okay, that's what and that's what generates this explosion in the variance of the estimate. Excuse me. And since gradient descent is making progress in the direction of the singular vectors that are not associated with such singular values, it kind of avoids that variance at the beginning, and it only starts experiencing that variance when it really starts converging with respect to those small singular values. So, you know, intuitively, it seems like there might be some advantages in stopping early on to avoid that variance. And this is exactly what early stopping achieves. We're going to analyze early stopping for this additive model, but I do want to point out that early stopping is actually extremely useful in machine learning in general, and in fact it's often used in deep learning, where essentially you perform early stopping based on some kind of validation set. There it's much more difficult to analyze what's going on with early stopping, although there are some works that analyze it for more complicated models. Here in our linear model, we're going to be able to understand very well why early stopping helps. And that's essentially the point of this lecture. So we're going to assume our additive model where we have a true vector of coefficients, we have the feature matrix, and we add some Gaussian noise. And this is what we train with. So we're going to perform gradient descent on this training data to minimize the least squares function. And then we would apply it on test data. Okay, that's the game here. We're going to focus though on an analysis of the coefficients. And in early stopping, essentially what you do is you only apply gradient descent up to a certain iteration k. That's the idea. Okay, so now in order to alleviate notation, where you remember that we had this to the k plus 1 for the kth plus 1 coefficient estimate. So here it's the kth coefficient estimate, so that's why we have a k there. In order to alleviate notation, we're going to call this tau j. So this is the expression that we have derived for the gradient descent iterates, except that, I mean, well, here this would be y. Okay. But in our linear model, this is our expression for the training data. So now we're going to see how this estimator looks like. Okay, so again, just to emphasize this, This is the estimate that we obtain if we run gradient descent on the training set, and we stop at the kth iteration. Okay, so as usual, we're going to compute the insert the SVD of X transpose there, and we're going to get some cancellations, and we end up with this expression where we have a term that depends on beta true and a term that depends on the noise. And this should probably ring a bell because this is not that different from what we had obtained when we were doing our analysis of ridge regression. So under our probabilistic model on the training data, we can ask what's the distribution of this. And we see that we have here a Gaussian vector multiplied by a matrix plus a deterministic term. The Gaussian vector has zero mean, so the mean is going to be that deterministic term. Okay, so this is the mean. And the covariance matrix is going to be just that matrix times itself. Okay, so remember, you have a zeta train, this random vector, which is obtained by applying a matrix to this random vector. If that random vector is Gaussian and zero mean, the covariance matrix of this whole thing is equal to the covariance matrix of zeta train, which in this case is the identity because it's IID Gaussian noise, times A transpose. Okay? And this is exactly what we see here. So now let's look carefully at both the mean and the covariance matrix, and we're going to look at them in terms of bias and variance. So when we look at an estimator, a first question that we ask is, on average, is the estimator close to what it should be, to this ground truth? Because in this case, we do have a generative model that tells us what the ground truth should be. And here, if you take this and you subtract beta true, you realize that you have a bias. Okay, we can express this difference like this. Okay, so I mean, you have to essentially expand this and realize that you can basically just express beta true in terms of the UJs, and you just get this term here, so that the difference between them, okay, is this. So this means that you have a systematic error on average, which is due to this term. Realize that this term is essentially decreasing in K, which shouldn't surprise us because we know that eventually we converge to the ordinary least square solution, which is unbiased, which does not have a bias, okay, which is right on average, which is centered exactly where you want it centered. So essentially we have a situation where the bias decreases with K. The analogy with ridge regression would be, in ridge regression, if you take your regularization parameter down to 0, then it's equivalent to ordinary least squares and you don't have any bias. But if you make your regularization parameter larger, in that case you start having a systematic error. And here we have a systematic error where when we take K to be small, because we have not converged to the ordinary least square solution. But as we discussed when we were talking about ridge regression, it's often fine to have some bias, to have some systematic error, as long as you manage to reduce the variance that is killing you in ordinary least squares because of these small singular values that produce an explosion in the coefficient. So if you look at this covariance matrix here, essentially this term in the middle is what gives you the variance in the direction of each singular vector of the feature matrix. And we immediately see that we have this issue where we have the square of the singular values here. And if we didn't have this term that depends on K, then this square of the singular values is what produces the explosion in variance in ordinary least squares. So now let's see what's up with that. Again, this is the variance. Well, now it turns out that, well, this is what I just said. These SJs are what blow up the variance. Oh, actually, sorry, this should be an I. I will fix that instead of a J. If K and alpha SJ are very small, then you can do a Taylor expansion and show that this term, is essentially equal to 1 minus k times alpha times sj squared. This holds when k and alpha sj are small. In that case, what happens here is that there is a cancellation and you end up, so when that happens, here you have 1 minus k alpha sj to the k, okay, which is equal to, oh no, sorry, this is the whole point, right? If this is equal to this squared, so you end up with this being more or less equal to k alpha sj squared, and again, and this is divided by sj squared, so there is a cancellation here. This is basically saying that when basically alpha sjk is, when k is small and alpha sj is small, then this term up here cancels out the effect of these small singular values. Okay, so the corresponding variance components is the variance of the noise times k alpha, but we are assuming that k alpha are small. So it turns out, as we had seen from the graphs, that for a small number of iterations, there is this cancellation, which, here it's a cancellation, but intuitively what is happening is that gradient descent has not converged in the direction of the small singular value, so that singular value is not having an effect. Okay. Of course, it's the only way of knowing exactly where you will have to stop is going to be by applying, by looking at validation error. But this shows you that for small k, you are decreasing the variance. And as we had seen, for small k, that's where you have higher bias. So there's this trade-off between bias and variance, and the way to resolve it and achieve the best result is just by looking at validation error like we saw in rich regression. So this is a depiction of what happens when we have a small number of iterations. Here we see a lot of realizations of gradient descent for different, here what we see is the following. The third iteration of gradient descent for different realizations of the least squares problem, where we have different realizations of the noise in the training set. So that's why beta 3 is actually the same for all of them. And at the beginning, what happens is that you haven't had time to make a lot of progress towards a solution, but the progress happens mostly in the direction of the singular vectors that correspond to the large singular values, because that's where we have fastest convergence, as we had seen. You have quite a lot of bias because the center is here. This will be easier to see. The center is here, so there's a lot of bias, but there's also very little variance here. Okay, like the estimates are not all over the place, there's very little variance. As you proceed, the bias gets better. Okay, like you're closer. The center of this distribution gets closer to the true coefficients, but your variance still starts growing. I mean, this is still under control, and this looks like a pretty good estimate where the iterations are 50. If you let it run up to 500 iterations, you get closer to the ordinary least squares situation where you're almost at the center, like you don't have that much bias, but you start having a lot of variance in the direction of the singular vectors corresponding to the small singular values. And essentially that's what kills you. So these are the actual, this is showing you a heat map of the Gaussian distribution that we have derived, so that you see that it corresponds to what we have just observed. We see that when we have at iteration number 3, we have quite a bit of bias, but not a lot of variance. The variance increases as we approach, as we increase the iterations, but the bias decreases, and eventually the bias decreases quite a lot, but the variance explodes because of the small singular value. So in this case, remember that you have a small singular value that is equal to 0.1. So now we're going to see what happens in practice when you apply early stopping to real data. And as usual, we're going to apply to this temperature estimation data set where we want to estimate the temperature in Yosemite from the temperature in 133 other stations. And for a fixed number of data, here I'm showing you what happens along the iterations of a gradient descent. At the beginning, we haven't made much progress, so we haven't been able to fit the training data. Eventually, we fit the training data well, and arbitrarily well, not arbitrarily well, but like we tend towards the ordinary least square solution, which fits it as well as possible with this linear model. The thing is that when the variance kicks in, we stop generalizing. Why? Because the coefficients are starting to fit the noise. They're starting to explode because of these small singular values, and that hurts our generalization because we're just fitting the training noise. However, in the middle, we seem to have a sweet spot where we're achieving pretty good generalization. Okay, and that's where we want to stay based on that's essentially how we want to fix K. We want to fix K so that we're at that point where we have good generalization. This is what happens to the coefficients for that particular example. At the beginning, they're very small because we haven't had time to make progress and fit. At some point, they're reasonably sized. These three coefficients are the ones that are largest when you do an ordinary least squares fit with a lot of data. So that probably means that they're the three most related other stations. And as you can see, at this point, they're the most they're among the highest coefficients, but eventually two of them actually do not become some of the highest coefficients when the variance explodes, because here the coefficients are essentially fitting the noise, as we discussed at length when we were talking about ridge regression. So stopping early allows you to stay at a point where the coefficients have reasonable amplitudes. And again, this is essentially what we learned from our analysis of the additive model, even though these are real data. So here there is no true additive model, although this does suggest that the additive model is a good approximation. So this is the selected number of iterations based on cross-validation, based on held-out validation error. And we see that when we don't have a lot of data, here on the left, you want to not run gradient descent for very long. When you have a lot of data, it doesn't really matter. You can run it for very long. You converge to ordinary least squares, but ordinary least squares actually achieves a good response error. So you're fine, as we had seen before. So this is a comparison between gradient descent and ordinary least squares. Eventually, ordinary least squares is good. Cross-validation actually tells you, well, just, as you have seen here, like you just converge essentially to ordinary least squares. You obtain a very similar solution. But here to the left is where we see the effect of early stopping, where thanks to the early stopping, we don't overfit the training data as much, and we manage to reduce this brutal generalization error that we incur essentially because of the fact that we're fitting noise. So here, gradient descent, early stopping applied to gradient descent achieves really good results. And interestingly, so these are the least squares coefficients. This is what happens when we apply gradient descent. So these are, again, the least squares coefficients for different amounts of training data. We know that when we have enough training data, they're quite reasonable. If we don't have enough training data, they explode. And gradient descent avoids this explosion, and that's why it achieves better generalization error. The effect is extremely similar to that of ridge regression. It's not exactly the same because the control on the coefficients is performed in a different way. In ridge regression, we have this additional penalty that increases the bias but controls the variance by penalizing large coefficients. In gradient descent, it's just that we don't give it time to converge and be affected by the small singular values. So it's a different way of pulling the solution towards the origin, but at the end of the day, the effect is very similar. Okay, the effect is very similar, and in fact, the results when you apply cross-validation between gradient descent, early stopping on gradient descent, and ridge regression, the results also on the response estimates are very, very similar, as you can see here. Okay, so what have we learned today? We have learned that gradient descent applied to the least squares cost function converges exactly to the ordinary least squares estimator. On the way, okay, if we stop it beforehand, it produces a biased estimate if you analyze it under a linear data model with additive noise. But that's not necessarily a bad thing, because this estimate balances bias and variance, and in particular the variance that comes from the small singular values of the feature matrix, because it doesn't have time to essentially fit the noise in that direction. And this is a similar effect that is achieved with ridge regression. So early stopping is a very effective alternative to ridge regression to avoid overfitting in linear models. And as I have mentioned before, it's actually useful beyond that in nonlinear models, and it's used all over the place in deep learning. Thank you very much.